Hello and welcome to the part 2 of the assembly language primer for hackers. Now in part 1 we went through quite a lot of theory about exactly how the CPU, memory, the stack, etc. work. In this video we will look at a live demonstration to examine these things in more detail. So if you haven't been through video 1, then please click on the link above in this page to view that video first before continuing. Okay, so let's get started. So we discussed a lot of things about memory organization, etc. In the last video. In order to understand these better, we will examine this using a simple C program. So it's called simple demo.c and it is downloadable from the same page. So what does this program actually do? Well, it's a very simple C program which takes in two user inputs to begin with using command line arguments and converts them into integers. Then it very simply gets a string from the user and then puts it back onto stdout. And then after that, it adds the two integers which were given using the command line arguments and prints them. The addition routine is called add and is also available in the same file. It's a very simple program. Now let's see how we can understand various aspects of memory organization to begin with using this program. Let's compile this. Let's give the -g GDB option so that a lot of more info is included for GDB to help us during latter part of the demo. So we get a warning that gets is actually an insecure function. That's okay for now. In later videos, we'll look at how this can lead to a buffer overflow and how that can be exploited. However, let's get back to the original demo. So let's run the simple demo program, give it two inputs 10 and 20. Okay, this is where probably the gets function is interrupting. Let's once again just write something. It echoes that back and it also gives us the sum. A very simple program. Now, let's run this program again and look at its memory organization, right? The program is running, it's waiting for our input. While this is happening on this terminal, let's go to another terminal. So in this terminal, what we'll try to do is look at the memory layout for simple demo, which is currently running. So the first part is to find out the process ID for simple demo. If you notice, the process ID for simple demo is 6024. Now, how do we view its memory layout? Now, one needs to understand is that the /proc directory in Linux holds all the runtime information about various processes and other things which are happening in the kernel. Now, an interesting thing is, given a process ID, you would find a directory, let's say 6024, corresponding to that process ID. And inside that directory, you would find various runtime things about that program which is running. So what we are interested in right now, in the process directory of 6024, which is the simple demo which is running, is the maps file. Now what this contains is the memory layout. Now as we can see, when we actually looked at this file, it gives us a dump of the various segments of memory, virtual memory, and to what they're assigned to. So if you remember, we said that if you go back to the presentation, that memory is organized and starts at 0804800 and then goes upwards. And the first section is actually the program code or the .text section, which starts at the base address. If you go back, we'll notice that this is exactly the place where the program code has been loaded, right? Then after that, we have various other segments. Of importance is the libc library, which has been loaded in these segments. And then finally, we have the stack, which is loaded at the highest point in memory, right? One important thing here is these flags. So what are important to us is the permissions these segments have. So basically R is read, X is execute, W is write. And this is how it is known which of these are readable, writable, or executable segments, right? So we can clearly see that this is the program code and it is an executable segment. Well, so this is how the virtual memory is organized. And if you kind of relate that to the previous slide set, what we said that every process is laid out in the same virtual memory space. Now, let's try and see if this is actually true. Let's go ahead, quit this program and rerun it once again. Then let's go ahead, find out the new PID for this program, which is 6029, and then view the memory organization again. So what we notice is, yes, once again, the layout for memory is exactly the same. It starts at 0804 8000 and then ends at this particular value. However, there is something very interesting you'd like to note here, is that the starting point of all the segments this time has changed apart from the text segment. Now, this is very interesting because if you notice, the last time the stack was loaded in BFF26000 started, that's where it started. However, this time it is starting at a different address. So why is this really happening? And the point I'd like to mention is that if you're seeing this, then most probably you're running Linux kernel 2.6 or above. And probably you're not going to see this in the 2.4 kernel. So let's actually just verify that with a uname -a. And if you notice, we are in the 2.6 kernel. So why this is happening is that in order to stop various overflow attacks such as buffer overflows, virtual address randomization has been implemented in the 2.6 kernel and above. What does this mean? Every time the same process is laid out, the segments will be randomized. That is, every time you run the program, the stack will not be located in the same segment to begin with. This makes it much harder to exploit vulnerabilities which rely on hard-coded value for the stack. So how do we go about looking at many of these things in a better way? So one thing we can do is, first of all, switch off the virtual address randomization feature in the kernel. We can do this very simply by changing the value of one of the runtime parameters in the kernel. The value which we are talking about is located in proc sys kernel, and then we have randomize VA space, which is virtual address space. Now if we just cat, what we will see is the current value of this is 1, right? What this means is, yes, randomize the VA space. However, we can change this setting by setting this to 0, right? So now what will happen is, let's say we run simple demo once again. Go ahead, figure out the PID, which is 6036. Look at the memory now. If you notice, the stack starts at BFF EB000, right? Let's exit the program again and then let's rerun it. Let's find its new process ID 6040, and then let's once again look at the memory organization. Now if you notice, this time the stack has been put in the same segment. just like the previous time. So now, because we have removed the randomization of the virtual address space, the stack is located, or for that matter, all other segments are located in the same predictable address space. Now, this is not just true for various instances of simple demo which we run. This is true for practically any program which runs on the system. Let's just run the cat program. So just waiting for some input, and let's actually figure out what is the process ID for the cat program which is running. Seems to be 6044. Now let's go back and look at the memory organization. And if you notice, once again, the stack and all other segments are exactly in the same place as were in the case of simple demo. So what have we learned? First, in this demo, we looked at exactly how we can figure out the memory organization of a process by looking at the proc file system. Second, we also noted that in 2.6 kernel and above, the virtual address space is randomized in order to thwart various attacks which rely on hard-coded addresses of various segment locations. Third, if the randomization of the virtual address space is actually stopped, then practically every program will have exactly the same layout of various segments in its program memory. So in the next video, what we will look at is using GDB to investigate more about the simple demo program. The reason why I have chunked it out into a separate video is that I don't really want to overload you with 30 minutes of a very long video. Well, hopefully you liked this video. Would request you to please leave a comment in the comment section below. That really helps me improve my future videos. Whether you hate it or like it, would appreciate if you can leave a comment behind. Well, that's all for this video. See you in the next one. Thank you.